Hi, welcome to Some of the Math Behind SciShow's There's a Loophole in One of the Most Important Laws of Physics, a bonus video on the Second Law of Thermodynamics. So, in the video, There's a Loophole in One of the Most Important Laws of Physics, by SciShow, it's pointed out that the Second Law of Thermodynamics has a loophole. It can be apparently violated by small systems. The second law says that the disorder of a closed system will only stay the same or increase with time, and will not decrease. The SciShow video, link in the description below, illustrates the second law using an example of the milk and espresso in a cappuccino. If the milk and espresso are initially separated, they will slowly mix over time, and once mixed, they will not unmix. The original unmixed state is a comparatively ordered state. All the milk is in one place, and all the coffee is in another. On the other hand, the mixed state is much more disordered, with all of the coffee and milk intermingled throughout the glass. The second law is fundamentally a statement about statistics. Understanding the cappuccino example touches on several topics discussed on this channel, like the random walk and the binomial and Gaussian distributions. Let's do a simple example to get a feel for the second law of thermodynamics and why it doesn't apply to small systems. Let's look at an example a bit simpler than coffee and milk mixing in a glass. Instead, we'll consider one set of n marbles in a box. We draw a line down the middle of the box, dividing the box into two equal volumes. We'll put the marbles in and jiggle the box. Then we'll ask how many marbles end up on each side of the box. Here, a highly ordered state is a state where a large majority of marbles are on one side of the box. A maximally disordered state is where half of the marbles are on each side. We'll see how the situation changes between a small system, where n is equal to a few, and a large system, where n is much greater than 1. While this is a bit different than the coffee and milk example, it is similar to other thought experiments posed in thermodynamics, like asking what the probability is that all of the air molecules in a room spontaneously move to one corner of that room. Now, you probably already have an intuitive idea of how this works out. If you put two marbles in a box, shake it, look inside, and find both marbles on the same side of the box, you probably won't be all that surprised. But if you put 100 marbles in the box, shake it, and find all 100 on the same side of the box, you'll probably wonder how that happened. Let's look at the math behind this intuition. For clarity, let's point out some assumptions we're making in this example. We'll assume that the box is jiggled enough to substantially move the marbles around, so the positions of the marbles change quite a bit each time we look in the box. We'll also assume we're jiggling the box in an unbiased way. For example, we don't tilt the box so all of the marbles roll to one side. We'll also assume that the box is big enough that the marbles don't interfere with each other. They aren't packed in so that a bunch of marbles on one side will squeeze other marbles out. So the location of one marble does not affect the locations of the other marbles. Now, we're just interested in how many marbles are on each side of the box. After the box is jiggled, each marble can be in either of two possible states. It can be on the left side or the right side. we take the probability of each of these states to be 1/2. As there are n marbles, and each marble can be in 2 states, the total number of microscopic states of the system is 2 to the n. As a marble's 2 states are equally probable, and the marbles do not interfere with each other, each of these 2 to the n microscopic states has the same probability, 1/2 to the n. Okay, let's pause for a bit of terminology. We use the term microscopic states for a state which specifies the side of every marble individually. So an example of a microscopic state is marble 1 on the left, marble 2 on the right, etc. Also, a macroscopic state will only specify the numbers of marbles on each side. So a macroscopic state could be 17 marbles on the left, 14 on the right. Note that a single macroscopic state may correspond to many microscopic states. Also note that we take every microscopic state to be equally likely. We do not do the same thing for macroscopic states. Okay, let's start with the case where there are 2 marbles in the box, so n equals 2. We jiggle the box and then look inside. What is the probability that the 2 marbles are on the same side in an ordered state? And what is the probability that the 2 marbles are on opposite sides in a disordered state? When we look in the box, there are 4, that's 2 to the n, where n equals 2, possibilities for the microscopic state we will find. First, both marbles could be on the right side. Second, both marbles could be on the left side. Third, they could be on opposite sides with marble 1 on the left and marble 2 on the right. And fourth, they could be on opposite sides with marble 1 on the right and marble 2 on the left. Note that these last 2 correspond to the same macroscopic state. If we choose a microscopic state at random, there is a 50% chance that it will be an ordered state with both marbles on the same side, and a 50% chance that it will be a disordered state with marbles on opposite sides. Let's say we jiggle the box and look inside several times. And let's say that one of these times we look, we find the marbles in an ordered state. If we jiggle the box and look again, there is a 50% chance that it will again be in an ordered state, and a 50% chance it will be in a disordered state. And if we start with a disordered state, the probability of getting an ordered state on the next round is also 50%. So for n equals 2, we freely move back and forth between ordered and disordered states. There is no tendency for disorder to increase. Because the number of ordered and disordered microscopic states is the same, the probability of observing an ordered state is the same as that of observing a disordered state. Now, let's consider the case where there are 10 marbles in the box, so n equals 10. There are a total of 2 to the 10, that's 1024, possible microscopic states. They are all equally likely with probability of 1 over 1024. First, let's look at the probability to obtain a maximally ordered state, all 10 marbles on one side of the box. There are only 2 microscopic, and actually only 2 macroscopic states for which this occurs. All the marbles are on the right, or all the marbles are on the left. So the probability is 2 times 1 over 1024, which equals 1 over 512. That's a pretty small probability. Now, let's find out the probability if we allow the minimum possible non-zero disorder. What's the probability that 9 of the marbles are on one side and 1 marble is on the other? First, how many microscopic states correspond to the macroscopic state of 1 marble on the left and 9 on the right? There are 10 choices for which marble is alone on the left. Marble 1 can be on the left with marbles 2 through 9 on the right, or marble 2 can be alone on the left, etc. So there are 10 microscopic states corresponding to the macroscopic state of 1 marble on the left and 9 on the right. There are similarly 10 microscopic states corresponding to the macroscopic state of 1 marble on the right and 9 on the left. So there are 20 different microscopic states corresponding to the 2 macroscopic states of 1 marble on one side and 9 marbles on the other. This gives a probability of 20 over 1024. By allowing the smallest possible non-zero amount of disorder, we have increased the number of possible states, compared to the maximally ordered case, by a factor of 10. So the probability of having 9 marbles on one side and 1 on the other is 10 times as big as the probability for them all to be on the same side. Let's take this further and see how many microscopic states correspond to each macroscopic state. We'll make a table for n equals 10 of the number of microscopic states for each value of the number, which we'll call m, of marbles on the left side of the box. Okay, so m is equal to the number of marbles on the left side of the box, which means that n minus m is equal to the number of marbles on the right side of the box. There are 11 macroscopic states corresponding to m taking the values 0, 1, etc. through 10. And the total number of microscopic states is 2 to the 10, which equals 1024. There are far more microscopic states where there are 5 marbles on each side, so m equals 5, or 4 on one side and 6 on the other, so m equals 4 or 6, than there are for the cases m equals 0, 1, 2, or 8, 9, or 10. The macroscopic states with m equal to 4, 5, or 6 are the ones with large disorder. The macroscopic states with m equal to 0, 1, 2, or 8, 9, or 10 are the highly ordered states. So let's say there are 7 marbles on the left side of the box and 3 on the right. We give the box a shake and take a look inside. There are far more disordered than ordered microscopic states for the marbles to move into. So the state of the marbles is very likely to move toward disorder and away from order. Now, you might be wondering how we got the numbers in our table a couple of slides back. We calculate these numbers using something called n choose m, which is written as n and m in brackets, and this equals n factorial over m factorial n minus m factorial. For example, above we used that 10 choose 1 is equal to 10, and 10 choose 2 is equal to 45. If you would like to know where these numbers come from, check out the video A Tiny Bit of Combinatorics, available on this channel. Now, let's imagine what would happen if we had 1,000 marbles in the box instead of 10. The probability for 999 of them to be on one side and one of them to be on the other side is 1,000 times as big as the probability for all of the marbles to be on the same side. It's easy to imagine that the numbers of possible states gets very large as the number of marbles on each side approaches 1,000 over 2, which equals 500. So the number of disordered microscopic states will completely swamp the number of ordered microscopic states. And now, let's consider the fact that a macroscopic system likely contains something like 10 to the 26 atoms. In a macroscopic system, the number of disordered microscopic states outweighs the number of ordered microscopic states by an astronomical amount. And actually, that's an understatement. We don't normally see numbers that large in astronomy. Okay. So, what have we seen here? If you have a small system with a small number of microscopic states, the numbers of disordered-looking microscopic states and ordered-looking microscopic states may not be very different. So if the system is in a state that is moderately disordered, it might move to a state of greater or lesser disorder. But for a macroscopic system, the number of disordered-looking microscopic states utterly swamps the number of ordered-looking microscopic states. So if the system is in a moderately disordered state, and it's given a jiggle, it is far, far more likely to get knocked into a more disordered state than a more ordered state. So, for a macroscopic system, the probability for it moving into a state of greater order is so small that we don't even consider it. This is why we say that the disorder of a closed system always increases. This is why the milk and the coffee won't move to opposite sides of the glass. There are far more microscopic states for a coffee-milk mixture than there are for coffee and milk on opposite sides of the glass. Okay, so lastly, in case you're interested in learning more, we'll give a few recommendations. Calculations to figure out the probabilities for certain numbers of marbles to be on each side of the box are closely related to a random walk and the binomial distribution. If you'd like to learn more about these topics, we'd suggest you check out the videos in the Random Walk playlist and the Binomial Statistics playlist, both available on this channel. Additionally, for large systems, the Gaussian or normal distribution is important. If you'd like to learn more about Gaussian statistics, you might want to check out the Gaussian Statistics playlist. And lastly, if you have any questions, feel free to ask them in the comments. If you liked this video, please like and subscribe, and thanks!